But if you're also someone that has like trouble like printing, then I can try and like figure out like where things are getting stuck. It should not take you a long time to print the tables into the CSV or Excel file. But so if it is, please let me know and please talk to me and maybe we can go through things in lab. Also go through another exercise of printing tables today. Also, if you find that you're getting stuck in defining the sample indicator, like who's supposed to be in your analytic sample, because you feel like maybe you missed a variable or something, like don't like try for hours. I know you can do that. just tell me, right? Send me your code, and then I can figure out like, oh, you missed a variable here, right? So I want to try and minimize the frustration of setting the sample and printing the tables. And so that you can focus on sort of doing more practice with interpreting regression coefficients and then running interactions, which I know can be like very confusing. It took a long time for me to get comfortable with it. There's some parts I still feel like I hate looking at it sometimes, but anyways. Okay, before I get started, are there any questions from last week that you think I should try and cover, maybe at the start or maybe at the end?
Paul, which data set are we using today for lab?
Unless I've made a mistake.
I was able to see the do file, the starter do file, but I was not able to see it.
Oh, really? It's not in the data. I didn't post the data file. Oh my god, sorry. Let me do that now if that's the case, which apparently it is since you're looking at it. Sorry, it was a very late night last night.
It's okay. It's okay.
Yeah. Oh yeah, you're right. The data file is not there. Sorry about that.
No, it's okay. No worries. It's okay. I'm just just asking to know which data.
Yeah. That makes sense. Let me put that in. Okay. It's uploading. And once I can confirm that you guys have downloaded it, we can get started. I also have to upload like an older version for people who are using an older version of Stata. Okay. It's almost there. Okay, can you guys see if the lab4 data is up there? Yeah, okay, good. Is Laura in here? Okay, she's not here, but I'm also putting up the older version just in case. And let me open up the lab file. Huh. Okay. And let me know when you have the data loaded somewhere, and then I'll know to get started. Were you guys able to load the file? Yeah. So I should get started now. Okay. Let me bring up the window. Okay. Let me share my screen. Here we go. So I just want to make sure that at the end of the lab, You know how to read a regression output. I think many of you do, but if you're unsure about anything, we can review things. That you know how to construct an equation from a table of coefficients, which is something you did for Greg's homework. That you know how to print and format the tables in APA formatting. And I'll cover how to do that at the end of the lab today. Like I think like half the people knew how to edit it in Word and other half didn't. And just as a quick reminder or announcement, in case you have not heard, all the UCI students get free access to Microsoft Office. So if you don't have it on your computer and you need like Word, there's like a free version that you can get as a student. And then I want to make sure that you know what it means to be controlling for a variable, if that's not clear yet. Okay, so let's get started. Someone made a suggestion that said they spent a lot of time like trying to figure out variable names and like whether the variable asked about in the problem set matches the variable that's in the data. And I know that you guys have access to the PowerPoint that sort of gives you a sort of a crosswalk of how the variable name, for example, math 6, matches onto like which grade they were when they collected the math test. But it's useful sometimes to like invest in like making the data label so that you can just use describe or whatever you want and not have to go back to the original documentation. And so I do that for you here. Like if we describe math, we can see that a lot of these are labeled, but not these two. So I've added the labels here. Same thing for read. We didn't label as read 6 and 7, so I do that for you here. I repeat for science and for general knowledge. It just makes it easier if you ever need to like figure out like what was math 7? It's 8th grade math. It's not 7th grade math, which is a confusion that it can be easily made. Okay. You can of course like create. Sorry, more stuff in the chat. I can't seem to get my chat window to pop up. So if it's for me, just unmute and let me know, or if someone else can let me know, that'd be helpful. And like if you can also create your own labels for other variables if you think that's useful. But I know that it won't be saved into the data set because I don't have your code running into my data. And so whatever data that gets uploaded is not going to have all of those labels. But you can basically copy and paste your code over so all of the variable labels stay with you. And while we're at it, I'm going to create all of the standardized test score variables in a loop. Makes it easier so that you don't have to create it on your own. The problem set is going to say like, because I've already uploaded it, like create a standardized version, but I just do that for you here. Into the loop, I put in all the test variables, and then I just use egen. But I wanted to show you something. Like if you look for the math, like you've already created some of them, right? And so if you run this loop, it's going to break, right? Sorry, right? It says zmath1 is already defined. And it would be very annoying if you have to go and remember like which math scores are standardized, which ones are not, and you have to pick out each one. There's an easier way to deal with it. You could think about like something like you could drop the existing variable into the loop, but this is also going to run into a problem, right? Because you didn't create it for all of them. So it'll say, well, zmath3 doesn't exist. It doesn't know how to drop it. And Stata has this like nice function called capture. It's not intended for this purpose. It's when there's an error, you see just like R111, it captures this error code. That's what capture is supposed to do. But a nice function that comes with capture, or like a nice feature that comes with capture, is it allows you to just move past the error. Like just keep going. Like, all right, I capture the error. It's stored in local memory, which you're not going to use, and then it'll just keep going. So if I run this, it'll now drop all of the variables that exist. If it doesn't, it'll just skip it, and then it'll generate it. This way, if now I look up to describe, you have all of these in here. anyways, so it's a convenient way of creating variables, but a problem is all of the labels that I created are now gone, right? Because I used dgen. It no longer says like whatever grade math, it just says math 1. So like the hard work you put into it kind of disappears. And also like I added some fancy code here, which you don't have to understand, but I've basically restored the labels this way. And I like added a prefix. And you don't have to know how to do this, but very quickly, all I'm doing is the same thing. I'm dropping the variable and I'm creating the variable. Same thing. What's new here is I take the variable from math 1 or whatever variable is on this list. I store it into a local called lab. And then I label the new variable with the std for standardized prefix and this lab variable. You don't have to understand this. But I had to run it. I had to put it in here, and I thought people were going to ask about it. All I've done is I didn't want these things to like go away and disappear, so I've added a label for them so you can still look at them. And then you see that like some of these old variables are in here. It's one of the limitations of using asterisk. It just specifies all the variables that start with math. So like math gain, which we had created before, either for a lab or a problem set. We don't really need that anymore. And if we ever needed them, we can create them again. So I'll drop them. You'll also notice there are these like weird variables with EST, which is short for estimate. This is probably running from coming from when you run like stab. You don't really want them either. And so I'll just drop these. Yeah. So like nothing here, I've just made life a little bit easier by creating the standardized variables for you and then labeling them so you don't have to go look for them. And to the extent that saves time, great. If, I don't know how much help it will be, but hopefully it's something. Okay, I'm going to quickly review quadratics. Right, you have done this like twice now for homework and for a lecture, but it's useful to sort of look at how to do it in Stata. And you are going to solve the exact same problem that you had to do for Greg through Stata, so it shouldn't be hard. For now, I'll create like a standardized version of SES. I'm going to use that as my predictor. This is our simple regression, regressing Z Science 7, which is, I think, 8th grade science test, standardized on ZSES. And we see that they are significantly related with 0.45, right? So this is kind of review. And now what we want to do is add in a squared term of ZSES, which will basically provide a threshold where you can like increase increasingly or decreasingly and hit a minimum or a maximum because it's parabolic. And creating a square term is pretty intuitive, right? Like SES squared is SES times SES. You just say gen SES squared is SES times SES. Right? Nothing complicated. And then now we add it in. But remember, we need the original term. Otherwise, it gets a little funky. Sometimes only the intercept changes. Sometimes the slope changes, depending on the sample and the variable you're looking at. And you have seen this before, like where's the threshold? Like a basic quadratic equation is y is equal to ax squared plus bx plus c. And then if you derive this equation, you get that slope, which is the derivative of y over, like in terms of x, dy over dx is equal to negative b over 2a, right? dy is delta y, kind of. dx is delta x. Change in y over change in x, that's slope. So slope is equal to this. And this is the equation that you use to get your slope. If a, the term in front of the a squared, which is here, right, is negative, that means the parabola opens down, meaning you have an upside down u. If it's positive, it opens up, you have a u shape, and so forth. You have seen this. Just review, just in Stata language, right? You can compute where the min or the max is by setting when x is equal to 0. I don't know why this is x. Yeah. Oh yeah. Sorry. Uh, you can. Sorry, I'm getting confused. You can plug into this equation these numbers, negative b, which is negative b, divided by 2 times a, which is here, and you can ask Stata to just display or print the results of a basic computation, and it'll give it to you. But there's another way to kind of do it. If you add to the regression command this option called coefficient L, which is for coefficient label, it'll tell you what these numbers, how these numbers are labeled. So if I display B, Z, SES, you get the same number that's up here. You can get the same number by doing the same thing just with the next label and so forth. So you could functionally, just using the labels, get the same answer as just typing in the actual numbers. And this becomes useful later, like when you're running a lot of loops and you can't like hard code your numbers into your code, but you could take the coefficient from this variable and then take this coefficient from this variable and manipulate algebraically. You don't have to do any of this, but this was just a quick review of quadratics, which you've seen before. And one practice we'll do is just interpreting what this means practically. So I'll rerun the regression. And if you are going to now, and I'll make this a little bit bigger. Like if you have to interpret this of the relationship between science and SES, what do you notice? Sorry, I'm gonna get some water.
I think we noticed that it's linear. The relationship is linear because like the coefficient of the squared parameter is very low, like 100. So it is not very significant. So it is mainly linear.
Yeah, like the magnitude is so small that it's not really changing the slope. It's more or less linear. That's true. If I like force you to interpret it as a quadratic, like how would you like? I guess it's a bad example since, as you note, like accurately, it is more or less linear. But if you were to describe the quadratic relationship, how would you then describe this?
Well, building on a means, so it's close to linear, but then it would be an inverted relationship because A here is negative and then B would be positive.
What do you mean by an inverted relationship?
Sorry, I'm thinking inverted U. I'm thinking of like it would have a like a facing down parabola.
Yeah. So how do you describe that relationship if the parabola is pointing downward?
As like for low, like I'm gonna make up, not make, let's just say for like 50. So between x is equal to 0, like books is 0 to 50, like you would see an increase, but then at a 50 marker, you'll reach a peak and then it will start decreasing. And then like the test score would decrease as you increase the number of books beyond 50.
Yeah. So I guess a shorter way that people often talk about it is sort of the relationship increases, but at a decreasing rate. There's a positive relationship.
I see what you're saying. I got you.
It is right. It's increasing, but like at a decreasing rate is how people often talk about it. Can you, like, looking at the like where the max is, the point in which like it levels off and there's like no relationship, right? There's no payoff to SES. That is at the x value of 17.75, in which there is no relationship between, or like functionally no relationship between SES and science test score. But what is the substantive, like practical look at understanding the max? Like what should you think as soon as you see this? Like, is that a meaningful finding or is that a non-meaningful finding? If so, like why?
I mean, it could be both meaningful and non-meaningful. I mean, in the sense that it's non-meaningful is because at that point you're seeing such a decreased rate getting there, like the rate at which that increase will happen is coming down. The way I'm at least thinking about it, it's like it's getting so low. So could you interpret that as saying like, where does it start really decrease? I mean, it's exponential, but I mean, like,
So
I
if
don't
I
know, like,
summarize what you're saying, I think you're highlighting the point about the slope being 0.
yes.
And actually, a slope of 0 can be a meaningful thing to say, right? Like, oh, they're unrelated, right? That's sort of a meaningful understanding and interpretation if you know that two things are unrelated. So that's still important, but there's something else that should like strike you as like, what's going on? Like, what is this? This is silly. We don't even have to pay attention to this. The mean and the max are sometimes important, but when you look at this, something should tell you like, we should ignore this. This doesn't matter.
I mean, I think we have to like pay attention to like what are the variables and what do they mean really. So like a 17 standard deviation like doesn't even make sense.
Yeah. Like, who is 17 standard deviation above the mean in terms of SES? There's no one. Like, you can summarize, right? like yeah, like even numerically it's not there, but like even if it was at like 4 or 5, it'd be practically meaningless. There's so few people 5 standard deviations above the mean that it's not a relevant, like it's nonsensical. This doesn't provide you with any like meaningful interpretation. So, but yeah, that's exactly right. Okay.
I have a question.
Yeah.
Sorry, kind of going back, why was SCS standardized? Was it because it was standardized in the article?
No. This was just an example. Like, if we use the regular SES, right? Maybe the ridiculousness of 17.75, right, would not communicate as much. Like, let's say I did this. I create another variable, SES SQ, SES times SES. Anyway, this is not the right variable. It's here. Let's say we put them in the raw units, and then I put into the regression the raw units. Then if you compute the same thing, here I'll get rid of the, I'll put in the right variable name to compute our, the point in which we have our max. Right, yeah, that's 14, but you don't really understand the SES composite measure. And maybe for some composite measures, 15 is possible. You don't really know what it means. I mean, you can look at the summary of SES and then still be able to like extract that it's kind of weird. A standard deviation unit sort of communicates how far you are from the mean very quickly and tells you how far off the X range you are. And this one just doesn't communicate as much. So it's just a way of like communicating to you the details of the X range. It's not required. And you can quickly try and like visualize it, like a quick and dirty like version, where you say scatter these two things, fit a line, and then fit a quadratic, and it'll show you something like this. And it's pretty ugly. This is not how you want to graph, but we will cover graphing better later. But you can kind of tell, like as Amin had pointed out very early on, this is very much a linear relationship. You are not so confident about the relationship down here. And then whether this linear relationship is not so clear from this scatter. Anyways, but it's just to give you a sense of this. You don't have to do this for the problem set, just giving you some basic graphing tools, and we'll get further into graphing tools later. Okay. Now, like interactions, we're going to examine how children's SES predicts their standardized science score in grade 8. And then we're going to add some controls, like controlling for grade 5 science score. We're going to control for age, gender, ethnicity. And we want to know if the association that we're looking at between SES and science is different by school type. Right? So the key interaction here is with school type. We have seen this. We've already created it. You don't have to create it anymore. We'll still use the standardized SES just for the communication of results. You don't have to. And then I said, for these control variables, should I standardize grade 5 science scores? Will this matter? Will this not matter? Like you know the regression, right? The regression is going to be some test score at grade 8, controlling for SES, predicted by SES, controlling for a bunch of stuff. Now, the question is, should you standardize these control variables? Does it matter? Does it not?
I think it won't matter in terms of the results since it's regressing variance, but when we look at the table, it would be better if we have it standardized to interpret it, I think.
Yeah, I guess it depends on the table, but you're right that it doesn't matter. It doesn't matter whether you standardize it or not. The variance is the same, so it will not change your model estimate. And since you're only interpreting your predictor, like it doesn't matter whether we do that or not. Okay, cool. Here's a quick summary. I want to put these into a global, these control variables, so that I don't have to type this out anymore. But notice that I've left out whites as the reference group, so they're not part of this list, so that when I run the regression, they're not in it. And also, of course, like we didn't really talk about it, but we could create a dummy for male, but we would kick it out because female is in there, right? And so this is also sort of like part of your reference group. Yeah. Now, the variable that we're going to use to like define school type is this CS type. It tells you whether it's a Catholic school, other religious school, other private school, and then it's a public school. I don't know what DOD BIA is, but maybe someone does. It's not an acronym, I know. So we're going to create a dummy for public school. Start out with an empty missing data. We'll give it 0 if you're non-missing, right? And then we'll give you a 1 only if you have 4 for CS type 2. Because 4 is public. And always double check to make sure that your dummy variables that you created, right, are mapping onto your categorical variables. I'll always do this check. And then we'll create our analytic sample indicator. Again, the cap drop is just in case I have a variable named something like this. I'll start with a 0. I ask that, you're not missing on any of the variables that we're looking at. And if you look, there's a lot of people that get excluded because a lot of people don't have all the information. So whenever this happens, you have to be skeptical about who's in your sample. And more on missing data and attrition in sample in future weeks. But just for now, just always look like how many people are in our analysis. 36% of the total sample. Not a good sign, okay? So this is not like a very good analysis, but there are ways to correct for it. It's not terrible.
What is the difference between cap drop and just drop for the lab?
So I'll drop it now, right? And I can't drop it again, right? Because that variable doesn't exist. And I sometimes put a cap in front in case I had created an indicator up front. And I can do this all the time, meaning there's no error. So it'll just drop it just in case, but it won't change the data in any way. Does that make sense?
Yeah.
So I'll recreate that.
Yeah,
Other questions?
Yeah. So it will do some sort of exception handling and things like that, right?
Yeah. It was meant to it was meant to get this error. This is like the type of error, so you can extract it and then continue. But yes, anyways, but I think you all get the point.
Yeah.
Yeah.
So
Okay.
I have another question. So what's the difference between like using 4 for the dummy variable and using 1? So like there isn't any difference, right? So just like
There's no
the
difference.
coefficient would be like a quarter of that like if we used 1 for it, right?
Yeah, I think so. Like if you gave all the dummies for all the race instead of a 1, like a 4, then you would have to adjust how you're reading the coefficients.
Yeah. So like it wasn't like very intuitive for me to like use 4 for a dummy variable. So I always thought it should be binary
Yeah.
or something.
Did we ever use 4?
No,
No, right?
I've
Okay.
always used binary.
Yeah. Okay, cool. Okay, so we'll run a simple bivariate regression. And I'll interpret this for you, which is simple, right? One standard deviation increase in SES is, it predicts 0.45 standard deviations higher grade 8 science scores on average. Note that the p-value here, I know it's a 0. It is not 0, it's just a very small number. If in anywhere you say p-value equals 0, someone will point that out and say that's wrong. And I have pointed out in some problem sets, but I figured out, but like reiterated here. So you would say in your writing, like p-value is less than 0.001 or something like that. Okay.
I'm trying to understand what we're trying to look at for the regression. So the school type is our moderator.
Yes.
And we're looking at if they're in public schools or not. So that's why we replaced the dummy variable only if it's 4, which was public. And we're looking at whether they're like Catholic or other religious.
Right. So our public indicator just captures them here. And then these 3 get a 0. I don't know if that.
Yeah. And we're looking at whether they're being in public schools or not moderates their SES and science relationship?
Yeah, that's right.
Okay.
Yeah, we just didn't get to the interaction piece yet. We're just like building a model from the bottom up. And just for practice, if I add in controls, like, and just as sorry, I'm not very organized today. Do you guys know all the numbers that are presented here? Is there any number here that you don't understand? Like I know I didn't cover all of them. Like it was like conceptually covered, but I realized we didn't like go through all of these. I'm sure you know what these are, right? But if you don't, please tell me. Do you guys know what these are? Okay.
Can you review root MSE? I think that's the only one I don't know right off.
Oh yeah. Okay. So this is mean squared error, and maybe a good place to start is it's what you do is you get all of the residuals, right? And you guys know what residuals are. This is the distance between the scatter and the best fit line, and it is the sum of all of them. So it's the sum of square residuals. Then if you divide it by the number of degrees of freedom, which is basically your sample size minus the number of estimator, minus the number of variables you have, you end up with a mean, an average, just this number divided by that, right? An average of your residuals squared. Okay. And if you take the square root of this number, you get this. But so this is how the numbers flow from here to here to here. But you have to first know what this is. If you don't know, I can explain.
No, I remember. Thank you. That was
Okay,
helpful.
Yeah.
So one more question. So
yeah.
because like it has roots, we have to like subtract the variables or not? Because like in a normal MSE, we don't really do that. It's just like a mean of residuals. I can't
Yeah,
recall doing that, like a MSE.
yeah. So because when you're getting the residual, after you compute the distance between the scatter and the line, sometimes you get a negative number, like you square it. And so by taking the square root later, it's not exactly the same because you square the distance, then you sum across. People want it square rooted, so it's closer to sort of reflecting an absolute distance. Because you're trying to undo the squaring, but it's not exactly the same. And this gets used in other places to sort of talk about like the amount of error in your like model. But like people really just look at this, yeah.
Yeah. I wasn't sure if just you said that you have to like divide it by the number of observations, subtract that subtract variables from that.
Yeah.
So like I haven't seen that.
Yeah. And this one is sum of square model. This is the distance between y mean and the best fit line. It just tells you like how much your best fit line is explaining the scatter. So if you were to take this sum of square model divided by the sum of square total, you would get your R square. And if this is kind of like uncomfortable for you, like this is feeling weird, I will come back to this later. But okay. But anyways, here's sort of like a dense technical explanations for people who already kind of know. I'll do like a friendlier breakdown of what these numbers are later. Okay, but sorry, I've like lost the thread. Can someone else who hasn't tried yet interpret for me this number?
I can't, it's the tells you by how much the standardized score for 8th grade will go up by 1 unit of increase in the SES standardized SES score.
Yeah, okay. And
With, and then in relationship to when I think we're controlling 7th grade age, female, Black, Hispanic, Asian, other in comparison to white.
Yeah, okay. Compare it. I would not say compared to white.
When we're holding them as the not control group. Oh my God, the comparison group.
So when you add control variables, it's not as clear who's in your reference category, like who you're being compared to. Like it's basically who's the constant. The constant reflects your reference group.
Okay.
When you only have dummy variables, say like regress Z science 7 on D female. Right? When you only have this with no controls, the constant is male. Right?
Oh.
But then if you start adding in control like age, that's now your reference group is now someone who has a 0 on D female, which is male, and then someone who has a 0 on age, which is someone that is 0 years old. And that's weird. And so what some people like to do when they want to actually interpret the constant is they'll take, say, like I would generate a variable called d mean age, which is going to be, sorry, let me summarize age. Age minus 5.7. I'll just do this really quickly. And like, just like, it doesn't matter if you subtract the number, like they're going to correlate perfectly. It's just translated. And so now someone who has a 0 on d mean age is someone with an age of 5.7.
I get you.
And so now if you regress these, let's see if I can find it, d mean age. Now someone in your constant is someone who has the mean age. So it would be the mean age male, which is different from here, right?
Right.
Which is kind of like a weird number. So, so like when you talk about it, like these are the controls. Like don't say compared to, because it's very hard to say who you're comparing it to once you start adding in many control variables.
Got you. Okay. Got you. Thank you.
Okay. Cool. Okay. Good. Looks like it was that was a useful stuff. And now I'm gonna now like add the controls and then run the regression only for the public school, right? And then I'll run the same regression for the private school. Sorry, maybe I need to make this a little bit smaller. Okay. So you know that now comparing these two numbers, and just as a reminder, this one is public school, this one is private school. Comparing these two numbers, what can you take away from it? Like what's important to take away from looking at these two numbers?
The top one's public, correct?
Yeah, and the bottom is private.
So in public, you're seeing a greater growth between SES and eighth grade science versus in private school when you control for those variables.
Yeah, the idea is right. It's better to say that the relationship is larger.
Okay, got it.
If you say growth, it means something else.
Okay, got it. So the relationship is greater.
Yeah,
between SES and okay.
Yeah.
So would it be correct if we say like that's like public school students benefit more from increase in their SES, something like that?
Yeah. You find that for kids in public school, right up top, there's a larger relationship between SES and science compared to private school kids, meaning SES seems to matter. It appears to matter more for public school kids, which could lead you to a hypothesis that maybe private schools are doing a good job of compensating for SES because it seems to matter less there. You can't say that definitively, but that's sort of the hypothesis like creation that you can like go down on. Question.
Wouldn't this be I'm sorry, would this be controlling for the differences between SES for public and non-public? Because if I just like think about it, I would assume that people who go to private school are in a higher category of SES and wouldn't be as variated in SES levels compared to public schools.
Yeah. So it could be a selection problem, right? Like just by virtue of selection, higher SES students select into private school, right? And so they're just already at a very high SES level. And at a very high SES level, there's a weak relationship between SES differences to outcome. Whereas at a lower SES level, which is public, there is a stronger there's a larger relationship. And so it could be reflecting sorting. Yeah, that would be exactly right.
So would we be able to compare these numbers like without any like assumptions or controlling for their differences in the first place?
So the short answer is these are non-causal and not fair comparisons. These are all descriptive and correlational, which could give you some ideas, but would never let you definitively say anything because you have all of these confounders. Yes, but there's a limitation to that, right? Like for you to have a causal estimate on one variable, you need one randomization. If you want a causal estimate on two variables, you need two randomization. Like the number of randomization you need, or like other random like variation you need, it's like 1-to-1 with the number of things you want to estimate, which is very hard to find. But it's important. And of course, Greg is all causal, and so am I. So yes. Okay. Now, this is like, you can run the same thing with BiSort. We've done this before. I'm gonna skip over that now. So up until now, it's really been like review, right? All of these things you've done before. And now what I'm gonna do is I'm gonna create the interaction variable, right? I'm gonna interact public with SES. And a convention of variable naming is that you put an X between the two variables. Of course, you could call it B public. I just call it public. It's okay, right? So it's just a multiplication. And then now I regress this. And just as a reminder, you always want to include the main effects. What happens if you omit it? We sort of cover that in class. And what we saw in class is that the intercept changes. Sometimes the slope changes. Sometimes it doesn't. It depends on the variables that you're working with. It's a lot more complicated than what we covered in lecture. If you wanted to learn more, you can go to like this site at UCLA, this exact one, and they like go through all the various scenarios if you're interested. But now, but I want us to interpret all of the coefficients here, and maybe one person at a time, or maybe one person can cover them all. But can you read for me, like, tell me like what these numbers mean? Or maybe it's better to say, like, if you wanted to know from this interaction equation, what is the relationship between SES and science test score for private school, how would you do it? Like, what would you look at? And if you, I'm sure like you're like getting confused now, right? A little, for some of you, it's one, people will often say, write out the equation, right? Y equals beta 0 plus beta 1, and then write all of them down. You plug in the 0 where it needs to go, and then you are left with like 1 or 2 terms, and then you can interpret it. Another way doesn't always work, and I'll show you why, but is for something as simple like this, we already ran this, right? For private school. This is private school, right? And you can, oh wait, no, that's not the right equation. Okay, there we go. So this would be the same thing, right? You're regressing science on SES, and then you're limiting it to only private school. And that tells you it's 0.23792. You run this, you will see 0.3792. So it's like another way, if you're getting confused with the equations, you can just make Stata do the thing that you want to see, and then like compare and match. And there's a point in which this breaks down, but this describes a relationship for private school between SES and science. How do you then get the relationship between SES and science for public school?
With the interaction.
So say more.
So the last coefficient means that like
This one? Or this one?
yeah.
This one?
No. Yeah. This is like the SES coefficient for the ones in public schools. So like when we multiply those variables, so public dummy variable is something that is like 1 for students who are in public school. So what it means is that their multiplication would be like a bunch of zeros, and the SES score when the student is in public school. So what I think it should do is like it tries to like find a relationship for SES and science when the student is in public school.
So give me a number. What is the relationship between SES and science for public school?
I think it's 2 for
this?
yeah.
It is Okay, and then so now I'm gonna like imitate like writing out the equation. Right? Science 7 is equal to beta 0, right? Plus beta 1 times ZSES plus beta 2 times D public plus beta 3 times ZSES times public.
Oh, you also have to
Plus
like
the error term. Okay.
add the other term for the public school, right?
What is the other term?
The public coefficient, right?
Okay, so you're saying if I add this and this, which is going to be something close to 0, that's the relationship between Z Science and SES for private school. And that seems off right now, right? Okay, let me say this.
Doesn't make sense.
Yeah, because if you remember, it was something closer to this, right? This is now the regression, right? Limiting it for public school. It wasn't 0. It wasn't 0. So I'm going to go back to the equation. I'm going to rerun the regression.
Yeah.
So,
But the thing is, sorry, the thing is there are multiple different stuff, right?
I'm not sure what you mean.
So like so the coefficients are not like multiplied to the same thing. So it doesn't mean that like it will be 0. So it's not like adding those two together and like multiply that to SCS, for example.
Okay.
One of them is multiplied to SCS and the other is multiplied by
That's
the
right.
public. Yeah.
So let's plug it in, right? This gets a 0. This gets a 1. Is that right? Because this is public school. D public is going to now take on a value of 1, right? Public is going to be 1, right? So this is really SES times 1. Okay. This is a constant, right? There's no variable in here. I'm going to move it over, right? It's a constant. Right? Just a new constant. I can get rid of the 1 here. It's not doing anything. And then I can, combine these two terms, right? I can say B1 plus B3 times ZSES. And that would be the same, right? And so you would have to add beta 1 and beta 3, which is you want to understand the relationship between SES and science, except when it's a public school, you're going to get a 1 here. So you have to combine beta 3 to beta 1. And if I combine them, and there's another way to do this, as you saw, but it's 0.48739848. Okay. Now I'm going to run this regression again, which is writing the same regression, but limiting it to public school. And it's 0.48739747. This is a rounding error. Okay, so are you with me? are you on the bus? If you're not, just tell me, and then we'll like talk about the confusion.
I don't know what I'm confused about, so I want to ask.
That's okay. That's okay.
I think I kind of understand like beta 1 plus beta 3 because we went over that in class yesterday, but I kind of lost you from the start till the end, and I only understood like lost you in between.
Okay. Yeah. So let's go through this again. I know I'll use the same like equation, right? Y equals beta 0, right? And I'll do it this way, like beta 1 times SES plus beta 2 times D public plus beta 3 times ZSES times public, right? Plus the error term, which you're not seeing, right? For someone in private school, for D public, they get a 0, right? And for someone in, again, private school, they're going to get a 0 here. But remember, this is ZSES times D public, right? This is what we're really looking at in terms of equation. if I multiply this by 0, this entire thing becomes 0. Are you with me? Yeah. And so this is also 0. And what you're left with is just ZSES. And another way to sort of look at it is, you know that the public person, right? Like this is just one variable, meaning if you plug anything in, it becomes a constant. It's not a variable. Here, these are two variables. If you plug something in, it remains a variable. And the variable of interest is SES. So really, you're looking at these two things. And when you know that public is equal to 1, this is going to be 2.24947. And so you add these two terms that are common. And when it's public, you know that this term is going to go away. And the only variable with SES left is this one. And this is the relationship between SES and science for people in private school. Confusion? All right. And I can come back to this as we go down.
Just to clarify, it's not private school, right? It's anything other than public school, because.
True, but so let me go back to the categorical term, which is here.
You had more than just private, public. There was like the other one you say you didn't know what it was, and it was like
Yeah. Well, Catholic schools are usually considered private schools. I haven't seen a public Catholic school. Other religious schools are also private schools, and then other private is just private. So the only records we have is, I mean, like I think there might be missing. Well, maybe there's not missing. But you see, right? Like private, private, private. They're called different things, but we are just calling them private.
Okay.
And now they're all lumped into one group. Okay, so now.
I'm sorry.
Yeah.
Like I'm a little lost, so I just.
Yeah.
That ZSES times public, that's the interaction variable?
That's right.
And why are we doing, like, just remind me why we are doing this? What was wrong with the good old regression?
That's right. That's a good question. Why did we do this? What's in here that wasn't why can't you just do this, right? Like your question is, we run this regression and we'll run it again for like private and for public, right? And you get these nice coefficients. Why bother? Why bother?
Yeah, why?
So we know that there's this difference, right? This one's larger, this one's smaller. And the difference is something like 0.25, right? And then now I will ask you, is this difference significantly different? Statistically significantly different? What if this was, instead of being 0.23, it was 0.40? Or what if it was 0.45? Is it significantly different?
So is that why we are doing that interaction?
Yeah.
So, but didn't we do that? Like, couldn't we like tell whether something is significant or not with a Tukey test or some sort of other test that we had before?
There is another test that's more complicated that we didn't cover in class. But no, there's no way to compare this. We know that this is different from 0, right? We know that this is different from 0. And I think what you're thinking about is an F test. But in order for you to do an F test, right? Like maybe the means of different groups are different, but they're all in the same model. So the only way for you to know whether this number and this number, right, is different, whether the relationship for private school or public school and private school is different, is to have an interaction term and see if that's significantly different. And this tells you that the slope is significantly different by this much. And I guess I already gave that part away, but like we didn't try to interpret this number, right? If you imagine two slopes, one slope might be steeper. It just tells you how much steeper, because it's the difference in the slope.
So the coefficient for the interaction would be showing us if there's a significant difference and the difference between the two slopes, because
Yeah, yeah, yeah.
My brain just stopped working. Sorry.
Yeah, I
So
know, I know.
showing the difference between public and private schools, the slopes.
Yeah. So, I mean, let's do a. How do I share a whiteboard? I'm gonna try to draw something with my mouse. Okay. Now we know how to graph this, right? Like here's one slope, here's the other slope. Just they're linear, okay? Right? And this tells you like this relationship is larger than this one, right? This is public, this is private. Okay. Now, is this slope, is this difference in the relationship significantly different? It's weird because I'm asking, is the difference different? Right? Like this, these two things, right? Like, are they significantly different? The only way to know is to run an interaction. I know it's like not like it's so easy or comfortable, but let's move on for now. Like but maybe I should still take a short break. Like we've been at it for like an hour. I'll take like let's do a 5-minute break, and we'll come back at 3:10, and I'll cover the rest. Okay. Up. Okay. I'm back early. We'll start in a minute, but looks like there's a question in the chat. I don't know if people are back, but I'll take a look.
Yeah, Paul, can I ask another question about the problem set?
Yeah, yeah.
So would it be, like, I'm looking at the problem set and I'm thinking that maybe I want to start with the interactions. Is there anything in the questions before that would kind of, some sort of changes in the data that I need to do that first and then move, or can I just like move on to the interactions and start from there?
That's a good question. I think you should be able to go straight into it, but let me check. Can I check that at the very end?
Yes, of course.
Okay,
Yeah.
and I'll give you a definitive answer, because I think I'm gonna have to take a minute or two to like make sure, so I'm not giving you bad information. So I'll do that at the end. Okay. Looks like there's a question. Or I
That
don't
was
know.
me trying to write the equations for what we just did, like adding equations. I wanted to see if this was right.
That looks right. Yeah, that looks right.
Okay, cool.
And then you can always like run the regression and check, but I think that looks right. Oh wait, sorry, that's not the thing I wanted to share. All right, sorry. Let's keep moving. Okay. So we just kind of went through this. Where is data? Where did it go? There we go. Okay. Yeah, I know like interactions take a while to get used to. So we just covered this, and then we didn't cover this, which is now all I've done is added controls. And nothing has really changed, right? The way you interpret it is very, very similar. Like, and this is the easiest one to interpret, right? Because this one can be talked about as the person who is in private school. And so how do you interpret this?
How much your science score would increase in relation to 1 unit of standardized SCS while holding constant of the other control?
Yeah,
variable?
well, yeah. For the person in private school, right? So controlling for demographic characteristics and prior test score, what is the relationship between SES and science score for someone in public school?
Why is that for public school? I didn't.
Oh, yeah. Oh no, this is for private school. So the question. This is for private school. Does that clear things up, or do you still have a question? Like, why is this someone for?
Isn't this
school?
for like? No. Oh, yeah, okay.
Yeah, this is the relationship between SES and science for somebody in private school, controlling for demographic characteristics. So the question is, what is the relationship between SES and science score at 8th grade for somebody in public school?
Sorry, can you explain why it was for private school for the ZSES?
Yeah. So do you remember up here, ZSES, right? For someone in private school, they get a 0 here, but that more importantly, they get a 0 here. If you multiply a variable by 0, you get 0.
We're good.
And so, okay. Yeah, okay. That's okay, I know. It's just, you're gonna hear the same thing multiple times for it to like sink in. Yeah, it's fine. So,
Thank you so much.
Yeah, so like we know that this now describes the relationship between somebody in between SES and science for somebody in private school. What is that relationship for somebody in public school?
You would have to add the ZSES and ZSES public.
Yeah, these two numbers.
Yeah.
Yeah, you would add these two numbers. Right, just like before, everything's the same, except in your interpretation, you know that you're comparing students with similar demographic characteristics and prior year test score. And then this tells you, right, same thing, how the slopes are different, or how the two relationships between the two, right, the relationship between SES and science for the two groups are different, how that relationship is different, and whether that's significant, and it is. You're just simply controlling for things, but your interpretation doesn't change, except for the comparison part. Okay. A quick coding thing, like if you don't want to manually create your interaction term, you can do this. You can regress your outcome on the two variables that you're using, right? dpublic and zses, and then put two hashtags in the middle. You have to say which one is continuous, right? And which one is an indicator to sort of say this is a dummy variable. So this gives you the same thing. And we can check 0.038, 0.038, so forth. So this is the same code to get what you got up here. Okay. Now you have to remember to put two hashtags. If you only put in one, it drops the main effects. Okay. So like if you do this, and there's sometimes a good reason to do this, like remember it's two hashtags, not one. If you only have one, it drops the main effects. Okay. Anyway, right. So the last bit is like, it was kind of like quickly talked about in lecture. And then like Greg sent an announcement, I don't know if you saw it, is the idea of a fully interactive model or a fully saturated model, which is, I'll run the regression so it's like in front of us and easier to see, right? Is that we expect, right, and now we know that the relationship between SES and science is different for people in public school and private school, right? But this public school, right, the way that, the way these control variables, right, relate to science can also be different, be moderated by whether you're in public school or private school, right? The way age relates to science, maybe it's different for someone who's in public school and private school, or maybe if you're female or not, or if you're of a certain ethnicity or race. And so what you do is you create an interaction variable for all of your control variables. So taking, right, you're multiplying one of your control variables with the public, right? This is equivalent to, like, I forgot what was in here. Right? This is equivalent to saying gen z science 6x public equals z science 6 times d public, and then repeat, right? This is the same thing. This is just a loop. And I, just so that you can sort of see where the end of our variable list is, if I run this, right, it creates now the z science 6 times public, age times public, d female times public, black times public, and so forth. Right? That's all that this did. I'm now creating an interaction between our public dummy variable of interest with all of our control variables. And I don't really want to type this out, so I'm going to use a global, right? I'm going to say take all of these variables from ZSES public to the other X public, okay? So I've now created a new global called interaction control, and you know, like, you can summarize it, right? Like it's the variables that we just created. Now it's in here. Okay, so I'm not going to type that out, all that out. I'm just going to use this. So now we run a fully saturated model, right? Regressing Z science on ZSES, on D public, all of our control variables and interaction controls, and you can check our interaction, our primary interaction of interest is here, just because of the ordering of the data. And of course, you can change this. Okay. And the way you interpret this is exactly the same, right? Like if we're interpreting ZSES, you're just controlling for more things. right? The relationship for somebody in private school, right, for SES in science is 0.57, meaning somebody in private school, being one standard deviation higher in SES is related to scoring 0.5 standard deviation or 6 standard deviations higher on the science test, controlling for demographic characteristics and their interaction, meaning the interaction of the control variables with being in public school. So everything is the same, except now you're just controlling for more things. So in your language, as you communicate this, you're saying the SES is positively associated with grade 8 science score, and you'll want to put in the statistics here, right? The beta and the standard error, or the p-value, right? Controlling for all of your variables and their interaction with being in public school. And we find, right, that the interaction, which is here, is now marginally significant. I say that because this is slightly higher than 0.05. Okay, so it's there, marginally higher. Now, I'll do a quick illustration for why you would want to run a fully interactive model and why in the field it's considered best practice, even though it looks kind of like a hot mess. Okay, we're gonna run the same regression, for public school with the controls, and for private school. Sorry, I'll note, right, for public school, remember, ZSES 0.0951. And then for, let me also write this down. Sorry. And then for private school, 0.057. I'm just writing it down here so I don't have to remember it. If I run only an interaction, okay, only a single interaction, like not fully interacted. If I now look at ZSES, right, this is supposed to be the relationship between SES and science for somebody in private school. That's 0.38 something. That is not what I thought it would be. That's not the same. If I add these two, right, that's 0.1025. That's close, but it is also not the same. Now, if I now run it with the fully interactive model, if I look at ZSES, it's 0.0575764. It's exactly the same. If I now add to this the interaction term, which is here, here, right? That's 0.0951302. That's 0.0951302, right? And so you can kind of tell already, right? When you have the fully interactive model, when you add controls, you can replicate the coefficients you got. And that's because your covariates are interacting with the public. That's why the estimates are changing whether you add the fully interactive controls or not. So it's kind of important because otherwise interpretation can change a lot. Okay. One more piece, and then I'll take questions. So now you can do a joint F-test, right? To ask, is the relationship between Z-Science 7 and ZSES and student characteristics systematically different for students in public and private school, right? That is like, is the model that explains, right, the current model with all of the controls, is that model for private school and that model for public school, are they systematically different? And the way you would do that is, like, a naive way of doing it, and it's often fine, is you would see if any of these are significantly different, and they are, right? This is significant, this is significant, this is significant, and you see, right, visually, public is now interacting with these control variables. They are significant. But when you run many interactions, and sometimes you'll have like 50 interaction variables, if you run 50 t-tests, you're definitely going to be rejecting some hypotheses, right? You're sort of like entering the realm of p-hacking when you do this. And so what you do is an F-test to say that are they all equal to 0 at the same time, right? The null hypothesis that they are not like that they're all 0, that there is no interaction. And then you read the F statistic and the probability, and then you conclude like, oh, in fact, they are different. But this is how you would do them. You would run an F-test on all of them. And you kind of knew that from looking at the regression table, but the F-test will sometimes give you a more conservative estimate. There are other uses for the F-test that I can't go into today, but you can just do this, right? Like this is equal to that. All of these are equal to 0. You could also do this. Like this is like the old Stata way. You run one test, you run the next test, and you say accumulate them, like this. Right? You just see the test accruing here. And in the end, you get 7.04. If you ran the previous code, you get 7.04. Of course, it turns out you could also just do this. And I just found out today as I was like getting ready. Like you could just name all the variables and don't have any of these equal signs. And it'll just assume that you want to test that they're all equal to 0, 7.04. And these are the nature of the test. Anyways, multiple ways to get the same test. You could use a loop, doesn't matter. And then of course you can just print these all out to a table. And I'm going to cover table formatting to, like at the end after I take questions. But this is, I want to make sure there's like more practice in here that we don't have to do. But I think I've now just covered all of the materials that you would need to do the problem set. But because today's kind of like a crazy day, I'm gonna like stick around for as long as you need me to answer questions, run practices, or like show you like something about the problem set, show you how to like format the tables in Word if you weren't able to do that. But for now, I'll take questions.
So one question here. So what sort of numbers would like indicate that these are they are the same actually? So these are like close to 0.
I think so. Like for the T statistic, right? I think it's like 1.95. I think for the F statistic, the threshold is something close to 4. Because like if you usually when you square the T statistic, you get the F statistic. I think the threshold is around 4, maybe 4, between 4 and 5. So if you see an F statistic that's like smaller, then you'll see that the p-value is larger. And we can kind of, I can show you an example F test. We'll just run one test. You can tell this is a very small F statistic. And so the p-value, and so I can fish around for something that's kind of there at the threshold. But you can look at the the F statistic table. But I'm pretty sure it's around 4.
Yeah, thanks.
Other questions?
It's kind of minor, but in the regression we did for before, like with the interaction control variables and without them.
Yeah.
If you could.
Let me find the thing. Oh, here. Okay.
I think it's after that.
Okay.
The fully saturated models.
Oh, yeah. Here.
Yeah, I think so. It's like, oh yeah. In line 297 and 98, why don't you put the if lab4 sample equal 1?
Because I'm stupid and I forgot.
Oh, okay. Oh. Okay.
I don't know how I got the same numbers, but yeah. But
yeah.
The point stands. The points. I was like, yeah. Yes, you're right.
But how would the numbers be the same as?
I think it's likely that both of both were dropping the same number of, like a similar amount of observations, because if you have to have non-missing on all of these variables. And so I think by here, I'm using all of the same variables. So even if I don't condition for this, you're probably gonna get dropped. Like if I do this, because the indicator is based off of whether you have non-missing values, right? So if I do this without the condition, the sample size is the same. Yeah. So I got lucky, but I should not have done that. But yeah. All right.
And one other thing was when we include all of the interaction control variables in the table.
Oh yeah. In the table.
When you run the regression with all of the interaction control variables.
Yeah, this one.
Yeah. So for the interaction control variables, if it's significant, would that mean that there's a significant interaction between the two variables?
Yes, it would. But just one note is, because you're like creating lots of these, chances are you might be finding a false positive. This is why you run an F test. And
the coefficients for the interaction variables wouldn't mean that much, or?
Yeah, so if you wanted to interpret this, right? That is, then you have to, this is the interaction between female and public, right? Which is like two dummy variables. So you would have to say, for somebody who is female and for somebody who is in public school, you can now try and get from that. Oh wait, sorry. This is
for a female in public school.
Yeah, for female in public school, and whether the relationship between public and C science is different for female versus male is what this gets you, and then it is. But it's like a different way of interpreting it, because it's a binary variable, but statistically that's what it's doing. Trying to quickly think of like the easy intuitive interpretation. But when you have two dummy variables, you're looking at mean differences. It's not really like it's not a continuous variation type of relationship. But if you want, I can try. But let me take another question before I try and interpret this. It takes some time. Okay.
Paul.
Yeah.
So when we want to like run a regression model, like with males and females pooled together, not like separately, we just have to like leave out the part that says the female equal to 1 or 0 out, right? Is that how we do it?
Let me make sure I understood the question. Like if you wanted to, let's say, regress the outcome on the female.
Yeah, we want to run a regression model. Like let's say we had a regression model before, but for separately for boys and girls. Now we want to run the same model with females and males pooled together. What does it mean, pooled together?
Okay. I see. So like if I regress, I think this is what you mean. Like let's say I regress this, right? Something like I'm looking at two relationships for a female, right? And then I'm looking at the same relationship for male. And if I pull them together, I want them in the same analysis, right? This only includes girls. This only includes boys. So I gotta get rid of this thing.
So right? Just that's it.
This because now like this is 4,000. This is 4,000 something. If I run this regression, now there's 8,000. But like you might be thinking about a question in which this is happening, or you're interacting female with something. The point about pooling it is when you condition on like an if statement, you're splitting it. By pooling it, you're just combining it so they're in the same analysis. So you get rid of the if statement.
Gotcha.
And for the problem set, you'll be adding in like more terms and interactions. But I'm pretty sure this is where you're getting it from. Yeah. Okay. Other questions? Okay, I'm gonna try to answer this. Then I'm gonna turn to Miriam's question about something about the problem set on whether you could start with the interaction piece and then turn to the tables later. And then I'm gonna talk about like, how do you format the tables in Word? And of course, I left that off to the very end because a lot of people already know how to do that. And so in which case you can just drop off, right? Okay, so let's say the female public. Female is gonna tell me, if I'm just reading female, the difference in the science score between male and female, right? Controlling for other characteristics, right? The difference between female.
In a private school, so.
Yes. Yes.
Because like for public would be.
That's right.
Female and public.
That's right. That's right. That's right. Yes. 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 Thank you. Yeah. So for people in, right, for a girl in private school, or for students in private school, the difference between male and female in their science score is this, meaning boys scored higher on science than female by this much. Now, if you were looking at the same kind of difference, gender difference for students in public school, you would then combine these two numbers. And let's just combine them. And conclude that that here in public school, female scores 0.02 standard deviations higher than boys do, right? In public school. You can kind of see me like, like it also takes me time, right? It's just how it is with interactions. Okay, now to Miriam's question. Can you do the interaction pieces first? Let me open it up right now. I'm really hoping there are no more mistakes on the problem set. Please, if something is not working out, you can first assume I messed up and make sure you ask me like, did you mess up? And I will give you an answer. Okay, so this quadratic piece is completely self-contained, right? You can do that. These tables, you have to create some of the control variables, and I'm looking to see if now here, okay, so you create all of your control variables here, you interpret them. Then for the interactions, you're creating your own, like a separate set of control variables, I think. Yeah. And then you run the interaction, then you do it pull together, and then you add the controls from here. Okay, so yeah, so you could do this section, like this second part first, and not worry about part one. And you'll notice, like, as you get here, like, I like ask you to like create these like standardized test scores, but as you saw today in lab, I just made them for you, right? To try and save you time. So that's that. And now I'll go over tables. Yeah.
So you said like you have created those the is that the standardized variables, right? Yeah. So right now in the data set for problem set 4, we can see them, right? Or you just did it, so they are not in that file.
Yeah. So Tiffany downloaded it as soon as I uploaded it. And then I did more work last night. And then on midnight, I uploaded new data. So unless you downloaded the data yesterday, right, it should be there.
Okay, I did it today, so it is there.
So it is there. And of course, if it's not there, then tell me and I will put it up there. Okay. 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 For the sake of the lab and for anyone who might still be like curious or interested, I'm going to go through like formatting tables. But other questions before I move to like formatting tables?
So was there a problem, like a problem in the problem set or something? You told I was like 5 minutes late. So did you talk about something?
Yeah, so I can air out all of my mistakes. So like I had some typos like in the problem set, like on the top as I was working on it, I wrote incomplete like as a note to myself.
Oh,
After
yeah,
I finished it, I forgot to delete it. And then instead of saying use like as per usual, like the file for PS4, it said something like use clean homework number 4. And then yeah, so stuff like that.
Yeah,
But-
yeah, just a copy paste mistake. Yeah,
Yeah. So
yeah,
stupid mistakes.
we've all
but yeah.
been there. Yeah.
Okay. Okay. All right. So I'm gonna go through tables.
A quick clarification question about the
Yeah.
homework.
Sure. Okay.
Sorry, I know I went to the homework. For problem set, for the first question, we're not including any predictors, right? It's literally just the Z Math 1 and the number of books in the home. We're not expected to look at the predictors that they used in the Artfire and Levitt article.
No. Just do only the stuff that gets mentioned here. So it's not exactly the same as what they did. Yeah, they also like you can't. It's harder to replicate the numbers because they use weights and they do other stuff like transformations that. Like, anyways, okay. I'm gonna do the tables.
Account for the missing values for number 1 because I know we do that in number 2, but I wasn't sure about number 1.
So I'm not sure I follow.
And you know what? It's fine. I should
Okay.
check first before I ask.
Okay. All right. So for whoever is on and whoever is watching later, I know it's been like an hour 40 minutes, but you know, like you can watch it whenever you want. Let me share my screen. There's some quick ways. So the table I'm gonna print, I might just run it from the top. Here is like this is now the regression without any controls. Adding controls but no interactions. Adding the interactions. Adding the fully saturated interactions. And then just as a reminder, STAB helps you print tables. They've all been named M1, all of these models. So I just say M star and catches them all. I'm printing it to this location at output, but if you don't want to, you could put like CD and whatever location and say using file name, that's CSV. B stands for beta, and 3 means I want 3 significant digits. You can put 2, and oftentimes that's fine. Standard error is SE. R square means also print the R square. No gaps means like they use like a default gap. It just sort of closes it, makes it like more compact. Label means use the variable labels. Replace means if this file is there, I just overwrite it. And then we can add the model titles, right? Like it's going to go in this order: M1, M2, M3, M4. I just say no control for the first one, control no interaction, control with interact. You can give it whatever label you want. This is the one I used. One thing to notice, is if you run this, and I'll pull this out, it's going to print many variables and probably more variables than you want. Right? It's going to give you a table like this. It's just too long, right? And sometimes you don't really care about this. And so you can tell STAB, like, okay, same thing, but only keep this ZSES, the public, and this variable. And if you print this, right, and then I'll say short, like as in it's not so long. It's going to print the same table, but it'll just be shorter because it'll only show you something like this. And the way to like move it, and the reason this is like, I really don't like STAB, but this is like the easiest one to like learn, is that if you have a comma, it moves it because it's a comma separated value. It's a CSV file, which stands for comma separated values. A comma is understood as a tab. So this was actually writing p less than 0.05, comma, p less than 0.01, comma, p less than 0.001. But it's a CSV file, so all of them get translated into tabs. Anyways, so you move this over to Word. And it's not so easy to look at. Oftentimes I'll use Arial Narrow. It just makes it more compact. Let's give it headers because you only use horizontal lines. One here, one at the top. We'll do something around here. We'll cut it off. That's where the coefficients end. Right? This is where the table really ends and the notes begin. And then put a bottom header here. You can use, sometimes it like, when you get it, the table is like much longer because there are a lot of spaces. You could use this up here. Sometimes you get a table that looks like this. Just go to the height and make it as small as possible. You can do something similar with the width too, but like sometimes it shrinks it too much, right? But you want the models up here. Yeah, I guess there's no way to like bring this down without changing it. So I'll just redo this piece. No border.
So
Bottom
we have
border.
to do this manually every time we make a table. I thought there would be a easier and simpler way.
Yeah. So I don't know if I'll have time for this. There are other programs that will help you format it into LaTeX format. But it's a harder package to like teach. You can learn it on your own and I can point you to some directions. I use a different one where I also add these like manual formatting, but the short answer is yes, but there are ways around it. And you know, you just go here, merge. Where's merge? Where's merge? I'll just do this. Why? Anyways, you can like merge cells, but
Yeah. So I think you have to go to the table design tab at the top. Layout. Yeah.
It's here. Yeah. Anyway, then you can like write this in, but I think I may have copied the table incorrectly. Like right now, the table stops here. So like, I like screwed up. Get rid of this. Add a new line. You know, add a line. Add the notes. The notes are really important, right? So like anyways, you've sort of seen like a bad demonstration of like a manual reworking of the table, which sucks. And yes, there are automations. It just takes time to learn them. But this is sort of like your solution. And so hopefully table printing isn't going to take you too long anymore. I know it took a while for some people when they first did it, but once you get used to it, it's like very, very fast. And that's what I'm hoping for.
Yeah? The tables that are in the problem set, like that means like my table should look like that. Like that's the best version of a table that can be like that. What is that? Like,
that is a good version that is APA formatted. That's the kind of table that you would put into like a publication.
So is it exactly for the questions that we have, or it's just it's a table?
As you saw.
Should I get the same numbers?
Yes. As you saw in the previous problem set, it's basically the answer.
Okay.
Right. And I want you to know that you got the answer so you can move forward feeling comfortable. And of course, if you didn't, you would tell me, and then I would help you figure it out.
So the table that you copied and pasted, that was a fully saturated model, but then you ended up deleting a lot of interaction terms, and that's completely okay. You can present it.
I did not. Oh, okay. Sorry. This is the fully interacted one. I'm just showing you these three coefficients only so that the table is not so big.
So if our table is about a fully saturated interaction, are we supposed to show every single possible interaction as well, or can we just delete it like you did to make it shorter?
So that really like depends on the reviewer, right? Like you submit a paper, they might want an appendix table that shows everything. Because some guy wants to see it, right? And so you show it, right?
Would you have to leave a note saying like this is not the full table that shows all the interactions or anything like that?
I mean, so in your notes, right, if you're not showing the control variables, you should be saying like the model controls for the following. The fully interactive model interacts all of the control variables listed with this variable. And so people, when they read the table, they know what that's about.
Okay, gotcha.
And oftentimes what you would, like the joint F test would end up in the notes. Like we ran a joint F test and found this F statistic, which had a p-value of whatever, which rejects the null hypothesis that the model is the same across the two groups or something like that. I think I will stick around if anybody wants to like do more practices with interactions, or if you want to like understand what's in the regression output. And of course, it's completely optional. Like no one has to stay. I just wanted to make sure you felt pretty good about where you are, and if you weren't, I would stick around.
Thank you, Paul.
Yeah, I think we have to see like in a day.
Yeah. Okay. We'll have office hours tomorrow, and I'll be there. And if need be, I will stay beyond the hour, right? So, and then of course, if at the end of Wednesday people are like, please show up again on Thursday, then I'll like show up again on Thursday. Like, I'll be around.
Paul, I cannot come to your office hours tomorrow because I have to take my dad to the doctors. Would it be possible for you to record it? Because I know that like most of the time the questions that other people have, I have the same question.
Yeah, sure. I will ask. If somebody says no, that's really hard for me, then I won't be able to record it.
I don't think anybody's gonna say no.
So if nobody objects, then yeah, I will record it. I will apologize in advance if I forget. Somebody will.
Oh, I'm gonna send you an email.
Okay.
Remind you to.
Yeah, I may forget. Yeah.
I'm gonna send you an email.
Okay. Cool. Other questions? Anything you want to ask, or?
I don't have any other questions. Is it something you want to tell me so I can like move faster with like solving these problem sets?
So I think so. For Tiffany, I'll stick around to answer your question. I guess for the general question, like it's hard for me to give you an answer to a broad question, but I think, sorry, it's my like. So there, you're gonna have like steps of like cleaning the data and setting the sample, right? And then you're gonna have the code that prints the tables. Those should not take you too long, but I know it can. If it's taking you too long, then you need to reach out to me or like other students and like explain what you were trying to do and what's happening so that you can quickly get over that. But I know like that's like not easy sometimes. The other parts of like coding a regression, which is very easier, it's like one line of code. Reading the interpretation is hard, and there's not an easy way to get faster at that. So I take your question as it sometimes takes a long time to code the cleaning and setting the sample and then printing the table. And with practice, right, you'll get faster naturally. In the beginning, if you're getting stuck and you just are like throwing up your hands and don't know what to do, then reach out to me or anyone.
Would you like to tell me like which part requires me to clean the data?
The problem set should make it very clear. Like we're gonna do this, then we're gonna do this.
Oh, okay. So it has already said that here you have to clean the data.
Yeah.
Okay. Thank you.
Okay, I'm gonna kill the recording and then answer other questions.
Thank you so much.